Hi everybody, this is Mrs. Schunzer,
And this is Mrs. Hatfield.
and we're ready to tackle 1.2 properties of real numbers. And our objective today is we're going to learn how to graph and order real numbers and also to identify properties of real numbers. And when we get into it here at the beginning, we got to go through some definitions. So the first one we want to talk about are just real numbers. And real numbers really are all the numbers you can possibly think of that you've been exposed to. They include both all rational and irrational numbers. And every real number that's out there can be a point on the number line. So from there then, we're going to get a little bit more specific and talk about natural numbers. And if you think about when you first were introduced numbers when you were a little kid, probably the first number you were ever introduced to was the number 1. And then from there you started to count. And so those include all the counting numbers. So like 1, 2, 3, 4, etc. After that, when you learn those numbers, then your parents probably introduced you to 0. What does nothing mean, or 0? So that leads us then to the whole numbers. So whole numbers include the counting numbers, the natural numbers, and 0.
All right, and then after that, we talked about integers. And integers add to the whole numbers, natural numbers, their opposites, and 0. And then from there, we go into what we call the rational and irrational numbers. And what's the difference between the two of them? In the rational numbers, all of the numbers that are part of this subgroup can be written as a quotient, and remember quotient is division, and that quotient is A divided by B. B cannot equal 0. We'll talk a little bit about that in the next couple of exercises. And we want to say that we're going to include terminating and repeating decimals. Terminating decimals, obviously, those that have a definite end in, as far as division goes, as far as that quotient of A over B. And repeating decimals where there's a definite pattern in the repeat of certain integers for that decimal part of the irrational number. The irrational numbers can't be written as a ratio. Their decimal representation cannot terminate or repeat.
So if I were to ask you what is the most common irrational number you think somebody would give you, what would you say?
I think that they might say like the square root of 2.
Absolutely. Another good one would be
Let's
pi.
say pi.
Yeah.
Miss that by the way, guys, that just happens to be Miss Schenzer's most favorite symbol in math.
Oh, I thought you were going to say dessert.
That too. All right, let's talk about the chart for rational numbers, irrational numbers, basically anything that we are going to call a real number. It's on page 12 in your textbook, so we thought we'd just crop it and put it in here so that you could see how does this all fit together in terms of a diagram. Okay, notice at the top left, we've got the natural numbers, or what we call the counting numbers. And then the whole numbers were the counting numbers plus 0. And then the integers were the natural numbers, and now we're going to add in the opposites and zeros. And then notice that at the very end there, at the bottom of that diagram, we end up with a split between rational numbers and irrational numbers. And those two subgroups are kind of something that you just got to get set in your mind. Rational numbers, they're numbers that you can write as a quotient. They include terminating decimals, like the fraction 1/8, being equal to the decimal point 125 and ending there, terminating there. They include repeating decimals. Example, 1/3, one of the most common ones that you recognize at first. 0.3 with that repeat sign above 3, meaning that that numerical 3 there repeats itself. Not the 0 part, but just the 3 part.
Can I just say something real quick? I want to emphasize the fact that 3 is really a rational number, right? Because you can write that as a ratio, like 3/1. So all of those subsets above rational numbers really fit into the rational numbers, right?
Right. All right, let's talk about irrational numbers. Irrational numbers have decimal representations that neither terminate, in other words, they never end, nor do they repeat in a special pattern. We talked about the square root of 2, and if you look at that, it's 1.41, 4213, and on and on and on. We talked about Miss Schenzer's favorite pi symbol and the decimal equivalent for that, which doesn't end at all. Cannot be written as the quotient of integers. In other words, when we talk about a divided by b, what happens is it doesn't end, it doesn't terminate, it doesn't repeat.
So here's a reference where we've shown you something from your book. In some instances for notes, we might just put in a chart and not actually fill it out for you, but we expect you to reference that and look at it and fill out your own notes.
Okay, sounds good. Okay, let's look at example 1 and read through it. It says, bankers and investors use the rule of 72, which is modeled by the equation y equals 72 over x, where x is the percent interest rate and y is the years it takes an investment to double. Which set of numbers best describes the number of years y it takes for an investment to double when x is a natural number? Well, if x is a natural number, 72 divided by x is going to give us a natural number.
Or a rational number.
A rational number. And that's your answer, is just the fact that it's a rational number.
Written as a ratio. Okay, so if you recall when we were describing real numbers, we said that you can graph any real number on a number line, and that's what exactly we're going to do in example 2. It says, what is the graph of the numbers -5/3, negative square root of 8, and negative 2.3 repeating? My recommendation here is to kind of get in the habit of maybe switching your fractions to decimals or mixed numbers. So -5/3 is the same thing as -1 2/3. That's easy enough to graph. I'm just going to go a little bit to the left of -1. Actually, it's closer to -2. So when you're doing this in your notes, make sure that you create a number line, put in reference points like your integers, label those so we know where you're at on your number line. And so I'm putting in -5/3 there. Negative square root of 8, I would literally just put that in your calculator. That's approximately equal to -2.828. So you're going to want to go close to -3 and put that in. And again, when you're putting it in your, either on a quiz or a test, if I'm asking you, make sure you put the dot in and label what dot that is. And the last one is -2.3 repeating. So that's going to be to the left of negative square root of 8. So I'm going to put it right there. And we'll label that as -2.3 repeating.
All right, let's look at example 3. How do the square root of 85 and 8.9 compare? Use the greater than or the less than sign. And here I'm going to recommend, just as we did in example 2, that you take the square root of 85 and put that in your calculator. You'll come up with approximately an answer of 9.22, and 9.22 is obviously greater than 8.9. And that's it.
Okay, so we took a copy of your page 14 chart and we threw it in here for your notes because we just really want you to kind of copy what you see here into your notes. And we're going to, as you're copying, we're going to talk about it. Opposite, think of opposite as also the term additive inverse. If you add something and its inverse, the opposite number, you're going to go back to 0. And 0 is considered your additive identity. It's what you add to something to get the same identical number. Reciprocal is considered to be your multiplicative inverse. So when you multiply by a multiplicative inverse or the reciprocal, you get back to 1, the multiplicative identity. And so reciprocal, if you have a number like 5, the reciprocal is 1/5. If you had 2/3, the reciprocal is 3/2. You're just flipping it, and sometimes I refer to it as the refliprocal. Closure,
okay,
going down to properties, closure. Closure just means if you're adding two real numbers together, you stay in the real number system. If you multiply two real numbers together, you stay closed in the real number system. Commutative means you can add two numbers in opposite order. So 5 plus 2 is equal to 2 plus 5. Multiply 5 times 2 is equal to 2 times 5. And I think of it like if I'm going from Monticello to Rogers, I'm commuting each day, and then I go backwards, Rogers, or actually I'd start Rogers, Monticello, Monticello, Rogers. And associative, you can group things differently. So A plus B, I can add those together first and then add C, or I can add B and C together first and then add A.
Okay, let's talk about identity, which we kind of talked about. Ms. Schenzer talked about that at the top of the page. Identity, if I add 0 to any number, it remains its own self. So 0 is the additive identity for addition. And then we have the number 1. 1 is the multiplicative identity, meaning that if I multiply any number by 1, it remains the same. It doesn't lose its identity. Distributive property. A times the sum of B plus C. I'm going to distribute. I'm going to multiply. Everything that's outside the parentheses gets multiplied by what's in front of the parentheses. So A times B plus A times C is the answer. Inverse, Ms. Schenzer just pointed out that I kind of skipped over that. So the opposite of A would be a negative A, or the opposite of a negative A would be a positive A. And when I add the two of them together, I get the additive identity. And likewise for multiplication, A times the reciprocal of itself is A times 1 over A. And when I multiply that, I get 1 as an answer, and 1 is the multiplicative identity. All right, example 4. What property is illustrated by each of the following equations? We're going to refer to the properties of real numbers up above here. XYZ equals XZY. Notice that the Z and the Y are changing places, so that's definitely a commutative, and it would be commutative for multiplication. Make sure you put in either multiplication or addition for each of these properties. All right, the second one, letter B, F times G in parentheses, then times H, and then F times in parentheses, G times H. Notice that the order stayed the same, but the grouping is different. We're still going to get the same answer whether I group F and G together or I group G and H together. So we're going to say associative, and again for the associative property of multiplication. Okay, the third one here, we have P plus Q times R equaling Q plus P times R. Notice that the P and Q are switching positions, and that's our commutative law, and it would be the commutative law for addition.
Here, letter D here, if you look there, the 5 plus Y switches order, so with the X. So this is commutative property of multiplication this time. So for letter E here again, if you see, we're switching the order between 8 and 0, and it's of addition, so it's a commutative of addition. This last one here, you can see that we have V plus 0 plus W equals V plus W. When you add 0, you get the same identical thing. This is considered the additive identity.